Hi and welcome to a quick video following up on this video that I made a long time ago, a really long time ago, a couple months ago, on integration with the z-scores. So in that video I said if you had a normal curve, blah blah blah, oh that's a really bad drawing, let's try and fix that a little bit. If you have a normal curve and say you've got your mu here, right, and your z here, then you can calculate the probability of something happening like up to this point by integrating from negative infinity to z of this integral 1 over the square root of 2 pi times e to the negative x squared over 2 dx. Now, I received a comment on that video which said that I should go in depth on how to solve that integral um, rather than just saying, that just getting the answer with Wolfram alpha or something, right? Unfortunately, this, being a follow-up video that's very short, I'm just explaining that it's actually impossible to do that by hand because the technique to solve this, right? The technique to solve an integral like this is, you have your Gaussian integration. Or rather, if there was a way to do this, then it would be over my head. I'm sure there is a way because the TI Nspire and other similar calculators can do it. Definite integral calculators. But by hand, it's something that I would not want to do. And the reason is because Gaussian integration is not that bad, but it assumes that you have this integral from negative infinity to positive infinity of yeah, the 1 over rad 2 pi is fine, but this e to the negative x squared over 2, right, dx, maybe we can just factor out that 1 over rad 2 pi. This is just constants, right? So it's usually just integral from negative infinity to infinity of e to the negative x squared dx, or just e to the x squared. Either is fine. And then you can solve that. But the thing is, because we have this infinity here, that's what makes it easy to solve. This z here makes it pretty much impossible to solve because we don't have infinity as an upper bound. In fact, when we are converting to polar to solve this Gaussian integral, which is how we solve it, right? We say we're gonna let this integral let this equal to I, right? So then we have I squared equals this double integral e to the negative x squared plus y squared, right, dx dy, where we say, dx dy, whatever, it's just going to be the same thing. And both of these are from negative infinity to infinity. I don't need to write that again. And then we can convert that using r squared equals x squared plus y squared. So it becomes e to the negative r squared, right? And then we have r dr d theta. The thing is, when we do this, right, if we go from like negative infinity to infinity, in our other bounds, right, then we're spanning the entire xy plane. So what we can do is we can say r is going to go from 0 to infinity, and then theta is going to go from 0 to 2 pi. The thing is, when we have 0 to z, right, first of all, we don't know what these bounds are going to be in polar. We really have no clue. And it's like there's the theta, it's next to impossible to say, okay, we're going to integrate from 0 to z over, this thing. Like, you really just can't, because here we have x, like, up to z, right? And then we're going to, I guess we'd have y from negative infinity to z here. And it's really weird, right? You can see how weird this would be if we're going up to here and up to here. What would it be like that? Like, you can't integrate over that. The reason that the negative infinity to infinity thing works is because we've got the entire xy plane. So when we have like r, r is going from 0 to infinity, right? This r wouldn't be going from 0 to infinity. We have no idea what it would go. It would go from 0 to something. We don't really. It's not possible to define it using polar coordinates, which makes it next to impossible to solve, or just it's really impossible to solve using this Gaussian integration technique. So that's why using the TI Inspire, the TI 84 Plus is much more viable of a reason, or of a way to do this, a way to accomplish this integral than doing it by hand. Already it's a pretty disgusting integral, um, but yeah, doing it by hand would be pretty horrendous. And there's really no easy way to do it besides plugging it into the calculator and getting an answer. So all right, so thank you for listening to my short uh, spiel on why it's impossible to do this by hand, and why one really needs to use a calculator rather than just plugging and chugging. Hopefully, if you are using calculus to solve your statistics problems, you're in advanced enough calculus that they let you use a calculator. Um, right? I know that in AP statistics, for instance, the College Board allows you to have a TI Inspire, CX, CAS, whatnot, with integration capabilities, and a TI 84 Plus is similarly capable of doing definite integrals. So really, there's no excuse, except, well, I guess you can't have negative infinities abound on a TI or TI 84 Plus, right? You can't really have that. But what you can do is you can put some number in your when you put that into your TI 84, you get this kind of these squares looking things, right? And then your dx, right? And then you can put in your function here. So obviously you'd put in your 1 over rad 2 pi e to the negative x squared over 2. And then this, because as you can see, this normal curve tapers down. So about here, it's close to 0. So what you could do is put a really big negative number. So like negative a million or something. That's basically in this context, very 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 similar to negative infinity. And then here you would still just put your z-score like we did over here. So that's what you could do. And yeah, it's just impossible to do it by hand. So all right, so thank you for listening, and yeah, I probably won't make a video for a while, but all right, see you.